So moving on to 4.4, we're starting to talk about applying the derivative to certain functions. So not so much anymore, what is the derivative, but how can we use it? And one of the most important applications of the derivative is using it to find local extrema. And extrema is just a fancy word that means maximum or minimum, and their plurals are maxima and minima. So we're using the derivative now to figure out where these points are. So what am I talking about when I'm talking about local maxima and minima? If I look at my graph over here, right, I can see these little peaks or valleys, right? So this would be a local max, this would be a local min, this would be a local max, right? I can see these points. So how do we interpret them now in terms of calculus? How do we put them in terms of derivatives, in terms of what we've already learned? So my theorem that kind of guides my first part of this section is to say that a function has a local max or a local min at some number that we're going to call c, if and only if f prime of c is 0. So if I take the derivative at that number and I get 0, then that tells me that I have either a local max or a local min. We just don't know yet if it's one or the other. Right, so let's kind of break this down, right? What does this f prime of c equals 0 mean? Well, if I look at my graph on the right, if I look at these maxima and minima, and if we're talking about the derivative, we're talking about tangent lines, right? So if I try to sketch in kind of the lines tangent to each of those points, right? Those, we call them turning points. We notice that their tangent lines are all horizontal, right? They're all horizontal lines, and that tells us that their slope at those points is 0. Remember that our derivative is a measure of slope. Horizontal tangents here. All right, so if we can find all the points that we have horizontal tangents, then we can find the points that we have local maxima or minima. That's all my theorem is saying, right? These are all the points that the derivative is 0, just to be consistent here. So what am I looking for? What are these points? Well, these points are important, so usually in math, if we have something that's important, we like to give it a name. So a critical point, or sometimes you'll hear critical number, is a number. We'll usually call that number c, just like we did above, and that c has to be somewhere in the domain of f, such that the derivative at that point is 0, or the derivative at that point does not exist. And IB, being the way it is, has a couple other names for it. So you may also hear turning point, which actually is something that you'll hear outside of IB as well. Like if you were to take calculus in college, you might hear that as well. But they also use the phrase stationary points, and that's something that even I haven't heard until working in this class. So if you see either of those phrases as well, it just means the same thing. It means essentially the zeros of my derivative. Right, that's all we're really talking about here. Maybe I'll choose a slightly different color. Right, that's all we're really talking about here are the zeros of the derivative. All right, well, how do we use the first derivative, right? We're starting to establish a connection here between f prime and the function itself and their, the local extrema. So how do we use it? Well, we have this first derivative test. And I think the best way to talk about this test is to lead by example and actually carry out a problem while we're talking through the steps. So I want to do a whole bunch of different things here. I want to find the x values of any turning points of my function. I want to know if these turning points are local maxima or minima. And I want to know whether the function is increasing or decreasing at a given point in time, or on the graph, I suppose. So we're going to work all this out in an example as we go. So that way I can kind of highlight the specific steps and highlight the specific results and then connect it to the problem. So to use my first derivative test, well, if I'm looking for local maxima or minima, I'm looking for points, as I said before, where the derivative is 0. So my first step would be to derive and set the function equal to 0. So we're going to do that. Maybe I'll do my my example problem in pink so it sticks out. All right, so my first step then is going to be to find the derivative. So I just have a polynomial function here. Everything I do is just going to be power rule. So 3x squared plus 4x minus 5. You can check that for yourself. And I'm going to set that equal to 0. Great, well, to find these critical numbers, I of course need to solve. Right, as I just said, this is going to give us our critical numbers. So I've got a quadratic here. I could try to factor it, or I could just use the quadratic formula, which is what I did. And I get 0.786 and negative 2.12 to stick with my 3 sig fig rule that IB kind of defaults to if it's not specified. So I've got my critical numbers, and now what? So I need to know a few different things. So if I look back at the problem, I've already established a couple things. Well, I've established one thing. Right? I've established the x values of any turning points of the graph, because we said before, turning points is just another name for critical values or critical numbers. Right, so here are my turning points. I'm going to want to determine if these are local maxima or minima, and I need to state if these are increasing or decreasing. We can do this at the same time. So step 3 is we're going to make a sign chart. We're going to kind of modify it from when we used sign charts last, but it's the same idea. So in order to make our sign chart, of course, we're going to test values when we do that. Test values within our intervals. And we want to keep track of the sign of the derivative. So let's do that. Let's make my sign chart. So I've got 0.786. That's not where that goes, because that is greater than my other turning point. So I have negative 2.12, and then I have 0.786. We, of course, know that the derivative at those points are 0. So I'm recording just the sign of f prime. I, of course, need to pick some test points. We're going to try to pick as easy test points as possible. So I need something less than negative 2.12, so we'll try negative 3. I need something between these two turning points, so how about 0? And something bigger than 0.786, so we'll try 1. So I would go through and plug each of these in. For the sake of time, I've already done this. So if I take f prime of negative 3, I wind up with a positive slope. If I take f prime of 0, I get a negative value. I guess I should be saying negative value, not negative slope necessarily. And if I plug in 1, I also get a positive value. So great, we've got this whole thing, but now what do we do with it? So we have some important results. The first thing I want to know, do like A or something, is to say that f of x is increasing when the derivative is positive. And I don't want to change letters yet. And then, of course, it stands to reason then that f prime is decreasing when f prime, or f is decreasing when f prime is negative. All right, so to answer another piece of my question, state the intervals on which f of x is increasing or decreasing. Well, I can conclude that f is increasing when x is on the interval either negative infinity to negative 2.12 or union 0.786 to infinity. Right, because in either of those intervals I have a positive derivative. Since derivative is a measure of slope, the function is increasing. So obviously the slope has to be positive, so is the derivative. And then of course f is decreasing on the rest of that interval, so negative 2.12 to 0.786. You may be wondering, why are these closed intervals, or sorry, open intervals? Why are these open intervals? Well, that's because if I were to include my turning points, I can't, right? The turning points are points where f prime is neither increasing nor decreasing. It's 0. So these are always open intervals. Okay, so there's another part of my question answered. Let's look at another important part of my results. Whoops. So I'll say some number c is a local maximum when the derivative of x goes from positive to negative. Maybe I should move that down so I have room to write. It goes from positive to negative around that number c. Similarly, c is a local minimum when f prime goes, well, the opposite case, right, from negative to positive around c. So if I go back into my problem and I look, and choose a different color again. So if I go back to my problem and I look at negative 2.12 and I say, what's happening around negative 2.12? I say, well, my derivative is going from positive to negative, right? It's positive until it gets to 2.12 and then it's negative. So I'm looking at a max. So I'll say f has a local max at x equals negative 2.12. All right, and what's happening at 0.786? Well, I'm going from negative, and it's negative until I get to 0.786, and then it turns positive. So negative to positive tells me it's a minimum. So a local min at 0.786. I want to look at this graphically for a minute before I get to the next problem. So I'm going to need some room here. Here's what I'll do. So I'm going to move this sticky later. No, I'm not, because it's the way. If I were to look at this graphically, so maybe I'll just sketch it in the corner here. All right, so if I just do a real quick sketch of this graph. So the graph that we just dealt with in the last problem looks like this. Here is my negative 2.12. Here's my 0.786. This is clearly not drawn to scale. But if we look at my results, I'll put points in as well so it's easy to see. F is increasing when x goes from negative infinity to negative 2.12, and then from 0.786 to infinity. So I can kind of see that, right? As I'm moving from left to right on my graph, I can see that the function increases until it gets to that critical value. Likewise here, if I start at that critical value, and I move to infinity, my function increases. Now if I look at between those critical numbers, it should decrease, like I said above. And sure enough, that's exactly what happens. Right, the function is going down. It's clearly decreasing. So I have a local max at 2.12, right here. Why? I mean, you can see it very clearly that it's the peak roughly in that area. And this kind of defends that result to say f prime is going from positive, right? So the function is increasing. The function is increasing here, and now suddenly it's decreasing. So I have a peak, I have a maximum. Likewise at 0.786, right? I'm going from a negative derivative to a positive derivative. So my graph is decreasing, and now it's increasing all of a sudden. So I have kind of a valley. I have peaks and valleys, so I have a valley. I clearly have a minimum here. So this is just my graph from above. I'm just going to make a note of that so I don't get confused. And now we'll move on to another example. So I've got a different type of function here. Right? I've got f of x is x over x squared plus 1. I want to find any turning points. I want to determine the nature of those points. So are they maxima or minima? I want to know increasing and decreasing. And then I have an extra step here. I want to talk about whether or not these points are global maxima or minima. So we'll talk about what that means in a minute. But first we're going to stick with what we know. Find any turning points. So to find any turning points, I want to know when does f prime of x equal 0? Well, I have a quotient here, so I should use my quotient rule. So I'll identify my u and my v. All right, so let's do some side work. So u is x, which means u prime is 1. I have x squared plus 1. So my derivative is 2x. So if I use my derivative, my quotient rule, I get low d high, high d low, divide by the square of what's below. And so I get, let's see here, I get x squared plus 1 times 1 minus x times 2x over x squared plus 1 squared. We're going to leave that denominator alone because it's not going to be relevant in a minute. And I'm just going to work a little horizontally here so I know I have some space. If I simplify this, I have, well, the 1 doesn't really matter, right? This is going to be minus 2x squared. So if I go through and simplify this, I'm going to have 1 minus x squared, 1 minus 2x squared over x squared plus 1 squared. No, I was right, 1 minus x squared. Okay, and this is all equal to 0. Now, of course, if I have a fraction equal to 0, then I just don't care about the denominator. The only way this is going to be equal to 0 is if the numerator is equal to 0, so this means 1 minus x squared is equal to 0. Of course, that means x is either plus or minus 1. So here are my turning points. Are they maxima or minima? Well, let's find out. I'm going to make a sign chart. All right, so now we're really applying the test here. So I have negative 1 and I have 1. I need some test values, so we're going to test negative 2, 0, and 2 because they're nice and easy. They fit right in the middle. And I care about the sign of f prime, so I'm going to plug all these into f prime, not f. So if I plug in negative 2, I get 1 minus 4 is negative 3. And then the denominator is always going to be positive because I'm squaring it, so I know that this is going to be a negative slope. If I plug in 0, I'm going to get a positive slope. If I plug in 2, same thing, I'll have a negative number on the top and a positive number on the bottom. So a negative slope there as well, negative derivative there as well. So determine the nature of the points, state the intervals in which the function increases and decreases. We can do these steps together. Right, so the first thing I'm going to say is that I know that f increases when x is between -1 and 1. And I'm going to say that f decreases everywhere else. Right, so from -infinity to -2, and from 2 to infinity. Of course, if I look, right, I'm going around -1, I'm going from negative to positive. So f has a local going from negative to positive, so f has a local minimum at -1. And then I'm going from positive to negative around 1, so f has a local max at +1. So are these global maxima or minima? Global, I need to think big picture now. A lot of times this would be helpful if you had a graph. You can just look at it and see if there's anything higher at any point than these. So what I would probably do here though, what I'd probably do is just graph it. But if you don't have a graphing calculator, you can do this by calculating the function values at -1 and 1, and then checking the limits as well to infinity and -infinity, just to see what happens at the ends of the graphs. But in this case, we have a graphing calculator handy, so I think it's fair just to graph my function, graph my original function, and see what happens. So, so if I graph x divided by x squared plus 1 on my graphing calculator, then I've got, that's not my pen, there it is. If I just do a quick sketch here, I get a graph that looks kind of like this, more or less. My artistic ability is not great. But what's important here is that you can see, so here are my local min and max. And you can also see that this graph doesn't go any higher than the local min or max, right? You don't see the graph trailing off this way. You don't see the graph trailing off that way. The asymptotes are within, kind of contained within where the min and max is. So these are actually also global min and global max, right? Because they are the highest and lowest points universally, right, on the entire graph, not just kind of in their own little neighborhood centered around the turning points. So this is all great. Working it algebraically is all great, but what about graphically? If I were just to give you a graph like this and say, tell me when the function is increasing, tell me when the function is decreasing, and then find the critical points. Well, when I give you, you have to pay attention to what function I give you. If I give you just f of x, then f of x is increasing wherever the graph looks like it's going up, right? Right? Where is the graph getting higher? That would be kind of up to this, whoops, I want the highlighter. That'd be kind of up to this point, and then it decreases, and then it increases over here. So where is f of x increasing? It's increasing from -infinity. I guess I should really say that this is a, and this is c, if I want to be more exact. From -infinity to whatever a is, and then from c all the way up to infinity. Right, and then it's decreasing, well, everywhere else. Right, here's where it's decreasing. So it's decreasing from a to c, not including a and c, of course. Because at those points, we have a horizontal tangent. We have a critical point, a turning point. And at those turning points, f of x, f prime of x is 0. So f prime of x is 0 when x equals a or x equals c. So it's pretty straightforward if I just give you f. If I give you f prime, you have to do a little more thinking, right? I need to use my first derivative test. So, well, if f of x is increasing, that means that the derivative is positive. So the derivative is positive anywhere it's above the x-axis. So here it is above the x-axis. So it's increasing from negative infinity to a and from c to infinity. And it's similarly, the function is decreasing when the derivative is negative. So anywhere I'm below the x-axis, so right here. So x has to be between a and c, and b is just in there to throw you off. So far anyway. Local extrema of f of x and classify them. So I need to look at my critical values, right? My critical values occur when the derivative is 0. So when is the derivative 0? At a and at c. If I look at a, I'm moving from a positive slope, or sorry, a positive derivative to a negative derivative. Right, so my function is moving from increasing to decreasing. So if I go increasing and decreasing, you kind of can even like try it out with your hand and go increasing up, decreasing down. I would have a maximum there. And then looking around C, I'm going from decreasing negative slope derivative to increasing positive derivative. So if I'm going negative to positive, then I have a minimum. So I can look at this graphically too and attack the problem both ways, depending on what I'm given. If I'm given a graph, I can use the graph. If I'm given a function, then I've got some work to do.